So in chapter 2 is where we introduce you to the concepts of forward kinematics. And for forward kinematics, what we want to do is know what the position and orientation of the end effector is in the terms of the joint variables. So in other words, I'm going to tell you what the joint variables are, and then what you have to do is tell me where the end effector is, its position and its orientation. So the cool thing about serial kinematic chains is that everything builds from our base coordinate frame, which we call x0, y0. So this is our origin over here. And then to go along this robot, you move a distance of the length, which is r1 here. And then this length over here, its length is r2. We want to know what is the position of the origin of frame 1 in terms of frame 0. This is what is x1. So we'll just drop this down here. We want to know what is x1 in terms of frame 0. And then what is, we'll drop over here, what is y1? And so this distance over here, we can get from the angle here. This is just r1 times the cosine of theta 1. So that's our answer, r1 times the cosine of theta 1. Whereas our height over here is r1 sine of theta 1. And then we want to know, well, what is the x2 in terms of x0 and y0? What is this origin point here? And so again, we can just drop this down. So what we want to know is, what is this additional distance here? Then we want to know the same thing for the y. What is this additional distance here? And so this distance that we have over here, well, we need to know what is the total angle that we've tilted. Well, it's first theta 1 plus theta 2. So this distance here is going to be r2 cosine theta 1 plus theta 2. This distance over here is going to be the sine of that quantity, r2 sine theta 1 plus theta 2. So the total distance is just going to be the sum of those two things. So it's going to be r1 cosine theta 1, r1 sine of theta 1, and then we will add in plus r2 sine of theta 1 plus theta 2, and plus r2 cosine theta 1 plus theta 2. Now that tells us the position at this point, but what we also want to know is what is the orientation. One way that you can represent the orientation is by telling what is this vector x2 in terms of the base frame, and what is the orientation of vector y2 in terms of base frame. So I'll take two numbers to describe this and two numbers to describe this. And so you can see right here, if I've moved my base frame right over here, so really I'm just caring about what is the relative orientation. So the total distance here is theta 1 plus theta 2 is my revolution there. And what I want to do then is take my x2, this orange variable here, and I want to project that. I want to project that onto my base frame. So I want to project it into x0 and y0. And I want to take y2, and I want to project that as well into x0, y0. So let's do the first one, this x2 projected into x0. So you see that's really just what is this distance here? And it's obvious that that's going to be the cosine. That's the distance in x we've moved of theta 1, theta 2. So I can write that in right here. Cosine theta 1 plus theta 2. And then my height over here, that's going to be just my sine of theta 1. So that is sine of theta 1 plus theta 2. Switch colors, and we want to know what is this y2. So my y2, if I want to know the x, I'm projecting that downwards. You can see that it's actually a negative distance. This angle right here, theta 1, theta 2. Again, this angle that I've gone over here, it's easiest for me to see what this height is here. So I'll do the bottom one first. That's again going to be the cosine of this number. Cosine theta 1 plus theta 2. Whereas this distance over here, this is actually in the negative direction. So that's the negative sine of theta 1, theta 2. And so now I have both the orientation of this coordinate frame, and I have the position of the origin of that coordinate frame, which is x2 and 0, y2 and 0. And then I have solved my forward kinematics. The next chapter, chapter 3, is all going to be about inverse kinematics. And inverse kinematics is figuring out, well, what are the joint parameters that I need to have in order to achieve the position and orientation that somebody wants. So already this is a harder problem. And somebody tells us where the end of the robot is, and we got to figure out where should the joints be in order to get there. And one of the reasons it's hard, even in this 2-link robot, we have something called the elbow up and the elbow down. So this is the elbow up, whereas over here is the elbow down. Both of them put the end effector at the same spot. This is the same distance. We'll call this C. Same distance C for both, same net angle, but the angles, this is theta 1. This angle here is theta 2, whereas over here, this entire angle here, this is theta 1, and then you'll notice that theta 2 wrapped all the way around here, theta 2. So there's 2 different solutions here, and we need to be able to solve for that. So it's time to dig back into our memory banks and remember the law of cosines. So remember, the triangle sides are A, B, and C, and the angle opposite C is theta C. Well, then C squared is equal to A squared plus B squared minus 2AB cosine theta C. If you don't remember this, there's a whole section of it in the appendix. It can remind you of all these. And then we want to know, what is this total distance C from here to here? Well, Pythagoras can help us out with that. This is the square root of x squared plus y squared. We want to know, what is this? Theta C. And well, we're given theta 2, but we're not given theta C in here, this interior angle. But that's easy to find out because that's just total angle for a straight line is pi minus theta 2. And so the cosine of theta C is going to be the cosine of pi minus theta 2. There's an identity that can help us with that. If you don't remember the identity, then you can build it from your sum of angles formula that you memorized in high school. So that's the way I'm going to do it here. Feel free to skip past that. If we say that this is the minus, we get the plus here, and then alpha is pi and beta is theta, and we get that this is the cosine of pi, cosine of theta 2, plus the sine of pi, sine of theta over 2. We get some simplification in here. This is going to go to 0, and this is going to go to negative 1. So this is equal to negative cosine of theta 2. Right over here is equal to negative cosine of theta 2. This distance, this R1 is A, R2 is B. I've got C over here, so I've got everything that I need in order to plug into this formula. Plug that in, we say that C squared is equal to x squared plus y squared. Then A squared is R1, so R1 squared plus R2 squared minus 2 R1 R2 times the cosine of theta C is really going to be negative cosine of theta 2. So let me propagate that negative through there. Now what we want to do is we want to solve for this cosine of theta 2. And so the easiest thing is to move everybody on the other side. So that's going to be x squared plus y squared minus r1 squared minus r2 squared, all divided by 2r1 r2. This ugliness we're going to name as a variable d. So that's the cosine of my theta 2. The sine by the parameter 1 is equal to cosine squared of theta 2 plus sine squared of theta 2. And so the cosine here, we can solve for that. This is going to be plus or minus the square root of 1 minus d squared. And the reason I've done this, do solutions. We want that because now we can have both the elbow up and the elbow down. And so then to solve for what my theta 2 actually is, I just take the inverse tangent of that. Remember, the inverse tangent is the sine divided by the cosine. So this is sine of theta 2 divided by cosine of theta 2, which you can write over here is tan negative the inverse of that plus or minus square root of 1 minus d squared divided by d. And then what you can do, and I'll leave that as an exercise for the reader, is insert what that d value is, which we have right here. Now we have both the elbow up and the elbow down solution for theta 2. Theta 1 I'm leaving as your homework assignment. It's worth figuring out, and it's kind of cute. The hint that I will give to it is to figure out theta 1. Well, you first assume that you have the answer for theta 2, and then you need to solve for what theta 1 puts your next joint in the proper position for that. So it'll be the sum. Theta 1 is equal to the sum of 2 tan inverse items. And so you can solve that out for yourself. All right. That'll take us into chapter 4. In chapter 4, what we want to do is figure out the velocity kinematics. Remember, velocity is equal to the position, and we just take the d dt of that. So all we need to do to figure out the velocity is we just take the d dt of our x position and the d dt of our y, and I've copied these from the previous, from our forward kinematics. And so you just take the time derivative of the second term. Now, if we look at it, the robot is not going to change how long its joints are, because this is a revolute robot. So this is a constant. In fact, the only things that could change are the theta values. And so we can write out what that solution is. If I take the time derivative of this first part, I can do my chain rule. Theta 1 is a value that can change. Take the derivative of this, that'll be cosine goes to negative sine minus R1 sine of theta 1 times the derivative of theta 1. But we also have this term is going to be those as well. That'll be minus R2 sine theta 1 plus theta 2 multiplied. Both of these can change. And then y dot is going to look very similar to that. So fortunately, sine doesn't change sign. So this is R1 cosine of theta 1 times the time derivative, how fast that theta 1 is changing, plus R2 cosine of theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. These things, especially when you have lots of joints, are going to get very messy. And so what we're going to do is do everything in this class in vector form. And so I'm going to say my full state of my infector is x, y. The configuration variables are the joint variables. So that's theta 1 and theta 2. What I want to do is say, well, how does my velocities of my end effector, how are they affected by how fast my joints move? And so what I'm going to do is I'm going to rearrange things. First thing I'm going to do is grab everything that's multiplied by theta 1. And so that's going to be this term here, and then got one term of this times theta 1. So I'm going to have negative R1 sine theta 1 minus R2 sine of theta 1 plus theta 2. And then I'm going to have everything that's multiplied by theta 2. Well, the only thing that gets multiplied by theta 2 is this one. So it's going to be minus R2 sine of theta 1 plus theta 2. And then the things times theta 1 for y are going to be R1 sine of theta 1 minus, got all this term here, plus R2 cosine of theta 1 plus theta 2. It is simpler as we go on. It's always gets simpler. Is going to be plus, that'll be just this term here, plus, so we'll put a comma there just so we know these are different terms. This is R2 cosine of the sum of theta 1 plus theta 2. These are the first derivatives. And like most of math, those have a name. They're named after a dead French guy. I'm going to call this matrix J. It is the matrix Jacobian. Jacobian means the first derivative. Second derivatives are Hessian. J for Jacobian. And so then we say that x dot is really just equal to J times Q dot. And there we have done our velocity kinematics. And so now we know if I move this joint at a certain speed, if I move theta 1, how fast does my end effector move? One of the things you'll notice is that this J is time varying. J is really a function of theta 1 and theta 2. All right, so you have to recalculate your Jacobian based on what configuration your robot is. But it's a linear relationship between how fast you move the motors, how fast the end effector moves. Now, we'll continue in chapter 4, the velocity kinematics. I've copied over my Jacobian from the previous time. Remember, x dot is equal to jq dot. This q is bold. And my q dot, then, if I want to solve for that, well, you might say, oh, all I need to do is invert this. And that's what we do. We just take the inverse of the Jacobian, x dot, and get the answer. We can only do this if j is square. So in practical terms, it's got to have the same dimensions. Q needs to have the same dimensions as x dot. And so let's just remind ourselves what the Jacobian of a 2 by 2 matrix is. A 2 by 2 matrix, what that is. Remember, it's 1 divided by the determinant of A. Let me tell you, I never knew why I was taking linear algebra until I started doing robotics. And so in my case, in my life, I took linear algebra only for robotics, but I get to use it all the time in this course, so that makes me happy. And then you multiply it by the adjoint, so that is dA, and then you flip the diagonal, and then negative b and negative c. Now this determinant of A, remember, that's just AD minus BC, easy to remember in the 2 by 2 case. And so the answer for that determinant, I'm just going to give here, and then I'm going to work it out here. But you can skip that part of the video if you want, because it's slow and tedious. But I'll work it out just for completeness. So all we do is we flip our A and D, so we can just write that down directly from what we have. So that's just R2 cosine of theta 1 plus theta 2. Then this term over here is minus R1 sine theta 1 minus R2 sine theta 1 plus theta 2. And then I'll change my colors because I can. And so then we just do the negation of these. So you can see this is just going to be R2 sine theta 1 plus theta 2. And this term over here will be my long one, which will be minus R1 cosine of theta 1 minus R2 cosine theta 1 plus theta 2. And so now the part that I promise you can skip is the determinant of this. Remember, the determinant is just AD minus BC, but you get R2 cosine of theta 1 plus theta 2, this quantity, times negative R1 sine theta 1 minus R2 sine theta 1 plus theta 2. It's our first term. Our second term is going to be minus negative R2 sine theta 1 plus theta 2 quantity times plus R1 cosine theta 1 plus R2 cosine theta 1 plus theta 2. And then we need to multiply that out. Negative R1, R2, I'll put the single terms first, sine theta 1, cosine theta 1 plus theta 2. It's my first term. And then this one times the second term, minus R2 squared. This time it's a cosine theta 1 plus theta 2 times the sine of theta 1 plus theta 2. And then my next term, I'm going to multiply this out. These negative signs cancel out, so it'll be a plus R1, R2 cosine theta 1 sine theta 1 plus theta 2. And then my final color here be this term times this term. So I get plus R2 squared cosine of theta 1 plus theta 2 sine of theta 1 plus theta 2. And here we say, all right, these two terms are exact opposites, so these cancel each other out. And so we say that this term, let's do it in blue, is equal to, now I can pull out the R1, R2, R1, R2, and just to be kind to myself, I'm going to pull the green term first and then the red term. So I get cosine of theta 1 times the sine of theta 1 plus theta 2 minus the sine of theta 1 cosine theta 1 plus theta 2. It's not so great. Well, the great thing is that I can do some substitution here. And so I'm going to say that alpha is equal to theta 1 plus theta 2. And we'll say that beta is equal to theta 1. Because these are the repeated terms that I see here. And then I'm going to flip their order so alpha comes first. So this is R1, R2 times this first term, sine of alpha cosine of beta minus cosine of alpha sine of beta. And we've got this property that if I have the sine cos, oh, that looks right, and minus this, that equals just the difference, the sine. And so we get this is equal to R1, R2 sine of alpha minus beta, which is equal to R1, R2 sine of alpha is theta 1 minus theta 2, and beta is theta 1. So we get is equal to R1, R2 sine of theta 2, which is what we wanted. Whew, we made it. So for in-class assignment, we're going to solve out what this d value is using the law of cosines. And then you've got a homework assignment where you're going to work on doing theta 1 and then solve these other coordinates out.